Hey guys, welcome to another A-level maths revision video. Today we're taking a look at some more Year 2 material, parametric equations, so involving parametric differentiation, found in Cartesian equations and such like that. Okay, so there's no parametric integration in this video. I think it deserves a separate video because it is quite tricky. So yeah, let's take a look at what we've got here. So all these questions taken from the old exam papers. So this first question here, we've got these parametric equations. So the first part, we just want to find dy by dx in terms of t. So, we've got the right pen colour. Where's my pen gone? There we go. So question 1 here. So to find dy by dx, what we require here is the derivative of x with respect to t and the derivative of y with respect to t. So if we calculate them separately, so if you just differentiate dx by dt, that's just 3. And if we calculate the derivative of y with respect to t, well, that's just the derivative of essentially minus 6 over t. And if you work that out, you'd get positive 6 over t squared, okay, or 6t to the minus 2. So we've got dx by dt, we've got dy by dt, but we need dy by dx. So how do we make this connection here? Well, if you take your dy by dt and we times that by dt over dx, notice essentially what would happen here is the dt's would cancel and we'd end up with dy over dx. Okay, so that's how we kind of connect these two differentials here. So dy by dt, we already know what that is. That's 6 over t squared. And then we times that by the reciprocal of dx by dt, so that's 1 over 3. So what we get here is 6 times 1, which is 6, divided by 3t squared. If you cancel appropriately here, this would give you 2 over t squared. Okay, so 2 over t squared there for dy by dx. For part B then, so we've not got tons of room, so if I just clear it, we know what the derivative here is. So if we just clear everything so we can start afresh. So if I start up here, we want to find the equation of the tangent to C at the point P. And we know P lies on C where t is equal to a half. So t is a half. So essentially what you need to do now is take this t point, a half, calculate your x coordinate, calculate your y coordinate, and then calculate the value of the derivative at that point. So if you work at the x coordinate first, using the parametric equation, that's 3 times t, where t is a half, minus 4. So that's 3 over 2 minus 4, so that gives us minus 5 over 2. Then the y coordinate at this point of t, so that's 5, minus 6 over a half. So that's 5 minus 6 over a half, so that'd be minus 12. So we get 5 minus 12, which gives us minus 7. Okay, so this point P here, that would be minus 5 over 2, minus 7. So all we need to do now is finally calculate the value of the derivative when t is a half. So we know dy by dx, that is 2 over t squared, and t is a half, so this is 2 over a half squared. So that's 2 over a quarter. And if you do 2 divided by a quarter, that's the same as doing 2 times by 4. So we get 8. Okay, so we've got all the information we need now. All we need to do now is work out the equation of the tangent. So I'm using y minus y1 is equal to m times x minus x1 here. Okay, where our y1 is the minus 7 and our x1 is the minus 5 over 2. So just substituting everything in that we need now. So because this is minus y1 and y1 is negative, this would be plus 7 is equal to m. So just note here, because this is the equation of the tangent, we don't need to change the derivative. If we're working out the equation of the normal, it'd be minus 1 over 8 for our gradient. But because it's just the equation of the tangent, 8 works. Times by x minus x1, which is minus 5 over 2. So that will also be plus there. Plus 5 over 2. And all we need to do here essentially is just start simplifying. We want it in the form y equals px plus q. So if I expand this right hand side, that's 8x. 8 times 5 is 40, divided by 2, so that's plus 20. And then if I take 7 off both sides here, we get it in the form we need. 20 minus 7, we get 13 there. Happy days. Y equals ax plus 13 there. And then finally for part C here, again another quite common exam style question. Can we show that the Cartesian equation for C can be given in this form here? So, part C, well, if we want to work out what y is as a Cartesian equation, what I need to do then is take the x parametric equation here, so x equals 3t minus 4, rearrange it to be in terms of t, and then substitute that t into my parametric equation for y. So, x equals 3t minus 4, so we could write that as 3t is equal to x plus 4, so therefore t would be x plus 4 over 3, so x plus 4 over 3, and like we said then, just substitute that into y. So y is equal to 5 minus 6 over x plus 4 over 3. So the 3 would go on top and times by the 6, so what I get now is y equals 5 minus 18 divided by x plus 4. But notice, we want to give it in this form presented in part C, so it's y equals ax plus b divided by x plus 4. So in that case, getting this over a common denominator then, I'm going to times 5 by x plus 4. So it's 5 lots of x plus 4 minus 18 all divided by x plus 4. Okay. Expand this part here in the numerator. So 5 times x, 5x plus 20, 5 times 4. We subtract the 18, and this is all over x plus 4 still. And then if we simplify the numerator, that just gives us 5x plus 2 all over x plus 4 there. Okay. So in that case, a is 5, and our b is 2. Okay, exactly as we need there. So that's the first question done there. Like you see, very kind of standard exam style question. As long as you're confident with all those kind of basic steps, it doesn't get too, much more difficult. But we'll see. The only kind of way they can get a bit more trickier is involving a bit of trigonometry. So that's where this question comes into play. So what we've got here is our parametric equations, but they are defined in terms of our trigonometric functions. So the first part, again, pretty standard. We just want to find the equation of the tangent, but in this case, it's made more difficult by the fact that we're working with trig functions. So, question 4 here. So we want to find the equation of the tangent at the point where t is equal to pi over 6. So just like we did before, what we want to do is we want to find dy by dx. What we'll also need to consider is the x coordinate, so that would be sine of pi over 6. And then we do the same with the y coordinates. That'd be sine of pi over 6 plus pi over 6, so sine of pi over 3. Okay, so we'll come back to that in a second. Let's work out the derivative first then. So remember, we work out dx by dt. So what's the derivative of x here with respect to t? Well, that's just simply the derivative of sine t. So hopefully nice and easy, that's just cos t. Let's work out the derivative of y now with respect to t. In that case, that will also just be cos again, so it's going to be cos. The derivative of the inside of this bracket would just be 1, so it's just cos t plus pi over 6. Okay, so nothing too difficult there. And then remember, to get dy by dx, we just do dy by dt times dt by dx. Okay, so if we do that, what would that give us? Well, let's consider it using t equals pi over 6. So using t equals pi over 6, in that case, dy by dx is going to be equal to dy by dt when t is equal to pi over 6. So that's going to be cos of pi over 6 plus pi over 6. And then we times that by dt by dx. So that's going to be the reciprocal of this here. So so 1 over cos t, so 1 over cos of pi over 6. Okay, so working these out individually now, this is going to be cos of pi over 3, so this is 2 pi over 6, pi over 3. So if you do this in an exact form, makes it a bit easier to work with. So cos of pi over 3, so that's going to be a half. And then times by 1 over cos pi over 6. Well, remember, cos pi over 6 is root 3 over 2, so we'd write this as the reciprocal 2 over root 3. Okay, so a half times 2 over root 3, the 2 are just going to cancel there and just give us 1 over root 3. Okay, so that's our gradient when t is pi over 6. So all we need to do, and again it's the equation of the tangent, so we don't do anything further with it. So all we need to do now is work out the x coordinate at t equals pi over 6, the y coordinate at t equals pi over 6, and then just use our standard equation for a straight line. So again, when t equals pi over 6, what we get in that case then is x equals sine of t, so sine of pi over 6, which we just know is 1 over 2, a half. Do the same with the y. So that's sine of pi over 6 plus pi over 6, so pi over 3, which we know again is root 3 over 2. So now all we do is use y minus y1 is equal to m times x minus x1. Okay, so this is y minus y1. So don't forget our y1 is this here, this is our coordinate, so minus root 3 over 2 is equal to m, well this is m, so 1 over root 3 times x minus x1, which is a half. And you can finish the question here. If you prefer, you can expand this right hand side, but you can technically finish the question here. This is the equation of the tangent. If we just write out one line further, by just expanding this right hand side, we get 1 over root 3x minus, so it's 1 over root 3 times minus 1 over 2, so we get minus 1 over 2 root 3 there. So I'm kind of squishing it in, but hopefully you can see. Okay, and you can write this in the form y equals mx plus c as well if you want, by adding root 3 over 2 to both sides, but it's unnecessary. You know, why make it more difficult than it needs to be? Okay, so that's part A there, that's the equation of our tangent. And then part B, just 3 marks for this, we want to show that the Cartesian equation is this given here. So, just like we always do, we're going to use our x, we're going to use our y, but the difficulty here is with it being trig, we need to kind of try and relate them, okay? And often the case is using trig identities, that's how we're going to relate them. So, the first thing I'm going to do is write out the compound angle formula for y. Notice it's t plus pi over 6, so we use compound angle formula. So doing this for y then, that's going to give us sine of t times cos of pi over 6, sorry, plus cos of t and then sine pi over 6. Okay, so we'll need that for our very final answer here when we give it in terms of y. So what we're just going to do now is relate x to y essentially using our trig identities. So using, in this case, the easiest one to use is sine squared t plus cos squared t is equal to 1. We can rearrange this in terms of cos t. So we just take sine squared t off both sides. And then we take the square root here. Okay, So cos t 1 minus sine squared t. Now don't forget, we know x is equal to sine t. X is equal to sine t, that's defined as one of our parametric equations in the question. So in that case, cos t, we'd actually write that as being the square root of 1 minus sine squared t, so that's x squared there. 1 minus x squared, like so. Okay? So in that case now, we know what cos of t is. What we can do now is just put everything into y. So in that case, y is equal, so using what we've just worked out here, sine of t, that's x, and we know cos pi over 6 is root 3 over 2. So what we get then here is root 3 over 2 sine of t. So we won't put our sine of t in just yet, we'll just write out step by step, plus sine of pi over 6 is a half, so this is plus a half of cos t. Don't forget we've just worked out what cos t is. We know what sine t is, so what we do is we just put this all together now. That gives us y equals root 3 over 2 times sine t, where sine t is x. And then finally plus a half of cos t, where cos t is the square root of 1 minus x squared here. Okay. Like so. And that's exactly as we're required to find there. Okay, so 3 marks for that. Just being confident with compound angle formula there, and just relating the trig identities to get it into the correct form. So being confident with trig is kind of important for parametric equations. It comes up quite often, so make sure you are familiar with it. And then this final question here, what we've got is again parametric equations, this time involving the natural logarithm. So in this case, we want to find the equation of the normal now, so slightly different to the other two. And then part B again, finding a Cartesian equation. So, question 6 here. X is ln t, y is t squared minus 2. So just like we've been doing previously, let's work out the gradient. And as you should be familiar with now, this is dy by dt times dt over dx. So if we work out each one individually, so in that case, if we do it up here, dy by dt, that's the derivative of this y here, this y parametric equation in terms of t. So that's just going to simply be 2t. And if we work out the derivative of x with respect to t, we get dx by dt. So in that case, the derivative of ln t is just simply 1 over t. So what we want to do now is just basically use our dy by dt and our dx by dt here. dy by dt, that's 2t. We times it by dt by dx, so that's the reciprocal here of this 1 over t. So the reciprocal of this would just simply be t. So 2t times t would give us 2t squared there. Okay, that's dy by dx for us. Now so we want to consider what happens when we get t equals 3. So when t equals 3, what we do again is work out our x coordinate, work out our y coordinate, and we work out the value of dy by dx at t equals 3. So if we do that step by step, when t equals 3, so x is equal to ln of t, so ln 3. Y is t squared, so 3 squared minus 2, so 9 minus 2, which is 7. So if we call this the point P, P in that case will be ln 3, 7. And then finally, working out the derivative at this point here, dy by dx, that's just simply going to be 2t squared, so that's 2 lots of 3 squared. So 2 times 9 is 18. Now just be careful here, like we've kind of picked up before, this is the equation of the normal now, so we can't use this value, we need the perpendicular, or we need the negative reciprocal here, okay? So the negative reciprocal would be flip this and make it negative. So this is 18 over 1, so it becomes 1 over 18. Then we take the reciprocal as a negative. So minus 1 over 18 is our perpendicular gradient. So we'll just write that down. So just to finish this now, all we do is use y minus y1 is equal to m times x minus x1, where our y1 will be 7 and our x1 will be ln 3. So this is going to be y minus y1, so that's 7 is equal, so this is minus 1 over 18 for m times x minus x1, where x1 is ln 3. And then at this point here, question done. You can expand if you want, but given that it doesn't ask for anything in a specific form, I'm happy to just leave it there. We get full marks for that. Okay, so that's part A done. And then part B, we want to find the Cartesian equation of C. So this one's really, really easy, just due to the nature of how simple our parametric equations are. So x is ln t. So x is ln t, and then y is t squared minus 2. Now in this case, what we always do is we write our Cartesian equation of c in terms of y. So all we need to do then is get x here. We need to rearrange this to be in terms of t, so it's t equals. So if x is equal to ln t, to get this in terms of t, I'm going to have to anti-log here. Okay, so exponentiate both sides. So what I get then is that t is equal to e to the x, just taking exponentiating both sides here. So if t is equal to e to the x, all I do then is sub this into y. So now sub into y. So if we do that, what we get then is y equals t squared, where t is e to the x, minus 2. And we can simplify this. If you've got e to the x squared, remember when you're multiplying here, just multiply through. So we got power raised to another power, we multiply. So this is e to the 2x minus 2 there. Okay. And that's it. Job done. So that brings us to the end of this video. I hope it's helped. No parametric integration. I'm going to cover that in a separate video. But if there's any issues, just leave a comment down below. Cheers.